Okay, let's begin. First, we are going to talk about the Darwin kernel. Darwin kernel is the kernel of all Apple operating systems. Was created in 2000 by Apple, based on BSD and Match with parts from OpenStep. You know that OpenStep was an open API created by Next and Sun Microsystems based on the work that Steve Jobs made in Next Computer. Because Next Computer is not solvent in financial way, Steve Jobs thinks about to make an open API with OpenStep with the possibility to work in Windows or even in Apple machines. And in this project, the result from this was OpenStep, and this is the core of the OS X operating system. It supports all Apple OS, macOS, iOS, watchOS, and tvOS, and maybe the next Reality OS, you know. It's an open source project, and it is a kernel that supports the AppKit or UIKit development APIs. You know that AppKit is from macOS and UIKit is from iOS and the other mobile systems like tvOS or watchOS, including the macOS interface Aqua, that it's the interface, the API for the interface. It's built in C and C++. Okay, it's the kernel, it's the core of the operating system, and it's the same core for all the operating systems from Apple. We are going more deeper, and for understand all the things about the security of the iPhone, we are going to talk in a brief secure history of the first iPhone, because I think it's very important to know the past to understand the present and the future. And we are going to make this brief secure history of the iPhone. Okay, today there is no doubt that January 9th, 2007, the world changed with the introduction of the first iPhone. Okay, but the first iPhone model, however, was far from the current ones. In fact, it was way less secure than the actual iPhones. For example, the iPhone Edge was a full-featured smartphone, but it had no apps. It's a closed device. When asked for apps, Apple's answer was web apps, not third-party apps that runs natively in the device. Apple defended to the hilt it was not necessary to have third-party software on the iPhone, and these closed functions were enough. The first idea about the iPhone is to make a device similar to an iPod with closed functions, not the possibility to expand it, but with more functions, but all the functions that the mayor of the users needs to work, for his device. But Apple and Steve Jobs was not sure about apps could bring something interesting to the users. And, well, for now, they speaks about to use web apps. The iPhone was totally closed in system and kernel. It's, like I said, a closed device. Otherwise, the inertial scroll, the pinch, or the capacitive touch screen were some of its milestones. And let someone talk about this.
With software. Now, software on mobile phones is like baby software. It's not so powerful. And today, we're going to show you a software breakthrough software that's at least 5 years ahead of what's on any other phone. Now, how do we do this? Well, we start with a strong foundation. iPhone runs OS 10.
That's the key.
Now, why would we want to run such a sophisticated operating system on a mobile device? Well, because it's got everything we need.
Good question.
It's got multitasking. It's got the best networking. It already knows how to power manage. We've been doing this on mobile computers for years. It's got awesome security. And to write apps, it's got everything from Cocoa and the graphics, and it's got core animation built in, and it's got the audio and video that OS X is famous for. It's got all the stuff we want, and it's built right in to iPhone. And that has let us create desktop-class applications and networking.
That's the most important key about the iPhone, because it runs OS X, and like Steve Jobs said, it's got awesome security. But the iPhone was software locked to what it has pre-installed, like I said before. And it used the Darwin kernel and the new Cocoa Touch library on top of it. It's an extensive framework with UIKit and other framework, other APIs like your session or core animation, core audio, and the other APIs that Steve Jobs said in the keynote presentation. The kernel being based on BSD is the same kernel that we said before, the Darwin kernel, that fits without any problem in its 128 megabytes of RAM that the iPhone has. Okay, but you know that native apps were programmed in Objective-C, and Apple, this is the most important thing about security, implemented digital signatures for code execution. And this is the way that we guarantee the security of the device. And to ensure this security, Apple used this own certificate authority to disallow the execution of code that was not signed off then on the system. Because of this, as you know, if you try to execute any software on the iPhone, even if you could compile a program for this, it's not executed because it's not signed by Apple. But do you know that Apple think about third-party software from the beginning? Yes. Let's read this. We define everything that is on the phone. You don't want your phone to be like a PC. The last thing you want is to have loaded 3 apps on your phone and then you go to make a call and it doesn't work anymore. These are more like iPods than they are like computers. This is the first way that Apple see its device. But Jobs add this. That doesn't mean there's not going to be software to buy that you can load on them coming from us. It doesn't mean we have to write it all, but it means it has to be more of a controlled environment. Steve Jobs said this on January 12th, 3 days later from the iPhone keynote presentation on the New York Times. As you see, Apple was think about the possibility of the App Store, but first they want to know if the iPhone will be a success or not, obviously. Okay? Well, but We are going to talk about the security of this first iPhone that it's way far from the actual security. Because of this, okay, the first iPhone has a cryptographic coprocessor. Well, it's so well because it needs to validate the digital signature of the software. It has two AES keys engraved in the chip, which cannot be extracted. A GID, a global key, which is the same for all the devices, and other that is unique for each device. The combination of these two keys makes the way for the cipher, for the cryptography, needs to encrypt or decrypt data or validate the digital signature of the programs. In the boot process, the GID and the UID keys are used to create the keys to be used by the device, and those limits its exposure. Okay? The passcode was recorded in the keychain with no hash. It's open. Even more, if you clean the record in the keychain for the passcode, you are open the iPhone, and that was passcoded to anyone. Okay? Well, this is the security. It's so easy. It was so easy to clean a passcode in the first iPhone, and obviously Apple was increment version by version the security of the device. The device keychain was and still is an SQLite 3 database, but most important, only the password elements were encrypted. The other was open in plain text. The encrypted elements were encrypted with the device key and a random initialization vector, but it was only one key for the whole keychain. Because if you make a brute force attack, you could extract the key and access to all the keychain and all the items, not only the items in the keychain, also the future keys in the keychain could be extracted if you make this brute force attack to this only key. I repeat, only for the password elements. The other are recorded in the keychain in plain text format. The iPhone OS 1 file system was not encrypted. Use a file system similar to the iPod, and you can you can see all the folders with an special software. But any executable, maybe the most important thing about the security of this iPhone, had to be signed by Apple to run on the iPhone. But maybe you are thinking about what is a digital signature? Okay, we are going to talk about it. The digital signature is a method to ensure that a certain file or data is not modified in the time since it was digital signed, okay? It is a method to ensure the integrity of a data and the fact that this was not modified. Okay, works in this way. First, we have a document, and then we are going to calculate a cryptographic hash of this document, a cryptographic hash that validates its content. Okay, we have this cryptographic hash. Then we used a private signing key from a certificate. The private key is used to encrypt, and the public key is used to decrypt. It's like you have the RAR or unrar, or FIP or unFIP. it's something like this, okay? You have two ways to make or extract, okay? With the private key, you can encrypt something. You can encrypt this cryptographic hash. But with the public key that you can put in something or give to anyone, with this public key, you can only do a decryption. You can't encrypt with this public. You only come to decrypt. With this private signing key, you encrypt the hash. Then, when you are encrypting the hash, then you are going to attach this hash to the document. And now we said that you have a signed document. Okay? Well, and then time goes by. And later on, we can check the signature and the integrity of a file with its digital signature attached on it. Well, the next step is to calculate the cryptographic hash without the encrypted signature part. We are going to recalculate the cryptographic hash because we need to know what is this hash for the file. And then we used the public key to decrypt the signed cryptographic hash. When we have the cryptographic hash and the decrypted cryptographic hash for the digital signature, we are going to compare. If these two hashes are the same, it means that has not been altered and is validated and has been signed by the authority that encrypted the hash in the first steps. That's it. This is a digital signature. Well, let's talk about next step. With the A7 comes the Secure Enclave chip. Apple evolves the encryption engine that has from the first iPhone to a multi-purpose chips intended for all security and encryption functions on the systems, including the biometric features, with a new security chip called Secure Enclave, a chip that is its property is a property of the kernel of the systems, as you can see. The keys never leave the chip to another context. The keys that the system uses or the biometric data for Touch ID or Face ID never leave the chip to another context. Secure Enclave is a black box, responsible for encrypting and decrypting any data, but you put a data on Secure Enclave and Secure Enclave returns the data with the encryption or the data decrypted. But you never know how this chip works internally. Okay? This is the most important thing. And we don't know what is this mathematical way to storage all the things about the biometry, the Touch ID and the Face ID. And other thing that Apple makes is to encrypt each file with an independent and unique key for each file, not one key for all the file systems. Okay? And again, all inside this Secure Enclave. Only the chip firmware is able to access the contents of the chip memory. Even if we read the memory, we will not be able to extract anything of it. some hackers and security investigators try to read this memory, but this memory it's not able to extract anything. The chip has an AES 256-bit elliptic curve cryptography key engine and 4 megabytes of RAM in its first version. With this, we have this black box and ensure all the checks about encrypting data, signing data, or biometric data, and all the things related to the security of the device. And obviously the system behaves in a very fluid way, because there is no weight for these tags on the system. Okay. We're going to talk about additional layers of security that have been incorporated over time. For example, access to user information, extensions, services, or even iCloud is controlled by digital signed entitlements. But what is an entitlement? An entitlement allows the app to use certain functions or obtain specific permission to run some services or features on the system. If you want to use something that is not allowed for certain functionality, you can activate this entitlement. In fact, Apple could authorize you for certain entitlements after you ask the permission for certain features. Okay? And these entitlements allows you to use certain kind of APIs that in the first way it's forbidden for you. For example, the iCloud or something else. Okay. Another thing that was implemented in the iPhone was ASLR, or Address Space Layer Randomization, that is incorporated in the system. This was a kind of security that is in each operating systems like Windows, Linux, etc. This function creates a table that shifts important areas of the system, such as the kernel, so that they are not always in the same place, and your process must have permission to ask about these tables to know what is the memory address of the kernel or other operating system important parts to access to them. Obviously, you are not allowed to ask about this in your app, but the system have this security to guarantee the security and the integrity of all the system. About this, iOS use ARMXN, or execute never. This is a way which marks memory pages as non-executable. If you put some code in the memory, you cannot execute this code. You are not allowed to execute code in any memory position in the device. Why? Because you need a valid entitlement of the associated app, but will be able to execute this code in memory. Each app has its own entitlement, and if a code is not from this certain app, is not allowed to execute this code in this place in the memory. Okay? This is the way that the system guarantees that you are not allowed to execute or to inject any code on the system to execute it if this code is not from an authorized app, that it was digital, that it was a valid digital signature. Okay. Another thing is about network communications. We're going to talk about App Transport Security, ATS. ATS is a set of requirements for securing network communications. It forces the exclusive use of your session and URL connection, even for third-party network APIs. Because of this, all the third-party network APIs are wrappers of Apple's native APIs. If you use AF networking or Alamo Fire, you are using a wrapper of URL session. Okay? From iOS 9, this set of requirements are mandates for things like the use of TLS 1.2 or even TLS 1.2.3 on all server certificates, 2048 RSE encryption or 256 bits elliptic curve key signed with SHA 2056 using ACDHE with firmware secrecy. This is a protocol to key agreement between two servers. You make a public key and send to another server, and this server makes another public key and send to you. And with this, you can create a key agreement and creates a private key that is shared between two sites from our server and the other server, or from our device to a server, and we have a private key that is different from each side, but you can use it to decrypt the same data with this public key associated. This is a key agreement protocol communication encryption. Okay? Allow exceptions for this. If you don't want to use a secure connection through HTTPS or another protocol, you can Apple allow the exception for example, multimedia content streams with AV Foundation that can do it in HTTP, or web view request, or maybe localhost usage, okay, when are working in debug mode, okay? All these things are mandatory standards since the end of 2016, which evolve year after year to comply with best practices in communications security. We must know all these rules to ensure the security of our app. Okay? Well, we are going to talk about data encryption. The use of data encryption is free to use, but with recommendations for Apple. For example, Apple does not recommend the use of RC4 or 3DES algorithms. Both are compromised and will be removed to avoid their use in future versions. For encryption, you must use AES GCM or ChaCha20, that is two encryption algorithms that both support from Apple's CryptoKit API that is available for the system from iOS 13. CryptoKit is a Swift native API for encryption. Also, if you work with Swift in open source, you can use Swift Crypto, that is the same as CryptoKit, but using the boring SSL Google engine to make the same things with the same specification, with the same interface. Because of this, you can work in encryption in, for example, server-side in Vapor, or in your app using Cocoa Touch or Cocoa with CryptoKit. These algorithms have the advantage of allowing not only encryption, but also checking whether the data has been modified. we can validate the integrity of any data that it's encrypt or decrypt with these algorithms. Also, all the files on the device are encrypted, and we have several encryption modes to set for each file that we can use when use the method save from a data type. For example, we are going to talk about these 4 system modes for encrypting data in storage. The first one is NS file protection none. There is no encryption on the data, it remains open even when the device is locked. However, it requires the file system to be mounted, because when your device is turned off, the file system is not mounted. It needs that the file system is mounted, and then anyone can access to these files. The next level is the NS file protection complete until first user authentication. As you can see, this name is from Objective-C, obviously. This option is the default for the system. It means that the file is encrypted and inaccessible until the device is unlocked for the first time when you put the first time your passcode or your password, okay? It also locked after 20 or maybe 44 hours, which requires re-unlocking with passcode instead of Touch ID or Face ID. Do you know that between 24 hours or maybe later, the device will ask you again for the passcode, and because the system re-encrypts all the file system and needs you to put your passcode again. Like I said, this is the default mode for all the files, and it's a mode that allows to access the files even when the device is locked, okay? But you must put the first passcode at the beginning. For processes that need continuous access to data, music, podcast, Bluetooth devices, geolocation, etc. Even if you have your device locked, your files are visible to the file system and the apps can access them, while the device is not in mode for asking you to put again the passcode. The next step is NS file protection complete unless open. In this kind of security, all the files are encrypted and can only be opened when the device is unlocked. When you locked the device, the file is encrypted and is not allowed to access to any app or any process in background. But there is one exception. Files are not locked or encrypted when the device is locked if they're being used. They wait to encrypt when no threat is using it. Imagine you have a background process and you locked the device. Well, if you lock the device and the file is using, the file is not encrypted unless it's closed, unless complete, unless open, okay? When the process is finished, then encrypt the file and the process or any other app cannot access to them, okay? Recommended for the process when you have uploading or downloading data over network, and which must be encrypted when the background process will finish, okay? And the perfect method, the method I use for most of my data, is NS file protection complete. NS file protection complete is the highest security mode, okay? Files are encrypted and inaccessible until the device is unlocked, okay? If you have your device unlocked, okay, your files are ready to access, but if you locked the device, then all the files will be encrypted, and it was impossible to access for any app or process, okay? Files are locked and any threats to them are cut off when the device is locked, okay? Recommended for most app data. How can you use it? How can you use this? Well, using this code. As you can see, you have a try data.write to URL, and then you use options. And in these options, you can put enumerations in an array. The first is atomic. Atomic is a mode that opens a temporary file to write all the data buffer, told the process to write the data buffer to this temporary file. And when all the data buffer is write to this temporary file, the temporary file is closed and then moved to the final location in the disk, on the location of the app, okay? This is a secure way to ensure that any other process cannot access to a writing process in my application. Also, you have complete file protection. Complete file protection is the last mode that we are talking. The mode that encrypts the file in the moment that you locked your device. Okay? This is the way you can use this. With all these things in our hands, we have to ask you ourselves, are our iPhones secure? No. No system is secure. Even with all present or future security features, no device is ever 100% secure. They never will be. Never. It's impossible. Okay? If someone says you someone says you that your iPhone or any other device is 100% secure, it lies to you. Okay? Every operating system and even hardware can have bugs in its design or its code that allow vulnerabilities to exploit it and do things that a system is supposed to be protected against. It's easy to understand what is a 0-day because it's a software that tries you not to do something has a bug, and this bug that allows you to do it. That's it. And there's no system without this kind of errors. How can I protect against this? Okay, the only way to be protected is update our system as soon as patches are released for the bugs that are discovered. But part of our responsibility as developers is to take into account best development practices that improve security and make it more difficult for cyber criminals to compromise our systems. Okay? If we do the right thing to make our app more secure, will be hard for these cyber criminals to compromise our app and our users' data. Okay? That's it. We're going to talk about Swift security, because Swift has security as its core. Why? Okay, Swift, like many other languages, is made in C language, okay? But Swift is strictly typed value-oriented language. But what does that mean? Okay, means that data is self-initialized to data types and isolates them by default. When you put a number 1 in your code, 1 is not a value, it's a type, it's a data type. That's because we are talking about value typed, because the values are typed and converted automatically into data types, because it's self-initialized and there's no values in Swift, there's data types. Because of this, you can infer. When you put let a equals 1, a is integer type because 1 is not a value. 1 is an integer type self-initialized. Okay? This is a value typed language. Okay? And is strictly typed. Because of this, the different data types are not allowed to work between them. Also, Swift runtime is static, is not dynamic, so it does not allow runtime injection of any elements. Because of this, when you work with TDD, with test-driven development, you have to create in code the injections or the mock objects, etc. You cannot use a API that injects dynamically, like Objective-C or even other languages like Java, because Swift has this static runtime and you cannot modify something, anything in the execution of your app. Collection types even is fully dynamic, so it avoids buffer overflows as its foundation. A string, data, an array, or dictionary has no initialization for the initial storage. It's all this kind of data are 100% dynamic. A string has a dynamic storage and creates more storage when it needs in real time. Okay? Because of this, it's impossible to do a buffer overflow when you code in pure Swift. Okay? The use of uninitialized variables is prevented. As you know, we all know the optional values. And is a compiler error for Swift, forcing a defined initialization or the use of optional values. As you know, all the data in Swift must be initialized before we are going to use it. Okay? And if some data, we don't know the data we are going to storage, then we must use the optional values. Optional values are uninitialized variables? No, because an optional value, when you define it, has an inferred initialization equals nil. When you put var something column int question mark and the compiler inferred equals nil. Because of this, all the data are initialized before we used. Okay? Also, code compiled in Swift is obfuscated by default. Any code compiled in Swift is not readable, is not accessible. You cannot read a compiled code in Swift because it's obfuscate. And obfuscation is when you change the name of the methods and the variables to something is not readable, like randomized characters, okay? You have a table, okay, for the corresponding names between the readable names and the non-readable name that it's obfuscated, okay? This table is the symbols. When you strip the symbols in Swift compilation, you're making this table, and this table later you have to upload, for example, to Crashlytics in Firebase to make the match between the obfuscated names and the names that the program used. Okay, this is the strip symbols functionality, the feature. Let's go and we are talking about insecure data recording. We are going to talk about best practices with data. We have to know that any data recorded in flat persistent is visible by anyone, such as using JSON, playlist, or even core data or SQLite databases. It is wise to audit the sensitivity of the data, okay, before developing and decide how it will be persisted and where, and if any data needs encryption or maybe any data have to be storage in certain locations, for example, the keychain, for avoid the access or read from anyone in the flat persistent, okay? Sometimes they are very sensitive data, okay, that either should not go on the device. For example, some data must be only in server side, and if you work with this data only in your memory, this data is secure. But if you storage in your device with a JSON, with a playlist, with a database, etc., will be visible in, like I said before, flat persistent, okay? Because of this, the best way to work with certain data is not to storage on the device, works only with server-side and with memory, or have their own container in the system to be stored. The keychain, health data, or maybe HomeKit data has its own container in the system and you have to use it, okay? Even more, the use of local databases should be properly encrypted. It's a best practice to make a transparent layer between your database, for example, with core data, or even when you store directly in your application a JSON file, maybe it's a good idea to make a transparent layer for encryption in these databases, okay? If you use Realm, for example, Realm has this feature, okay? You can set an encryption key on Realm and then all the data in this database will be encrypted and is not visible to anyone that try to read the database, okay? But with core data, you must create this transparent layer for encryption and decryption. It's not so hard because you can use extensions for the data types, okay? But well, you must do it. It's your responsibility. If we persist, for example, an enumeration that is part of a sensitive data set, we should not use its value as a string or sequential numbering, okay? If you use an enumeration and you are typing with string, it's more secure to put strings that is not equivalent to its value, okay? Because of this, when someone read your code, when someone read your data, they don't know the equivalent of these values, okay? More. Now we are going to talk about data encryption and hash calculation, okay? Maybe you are thinking about to use encryption. Okay, we are going to see it. The first things we want to know is cryptographically secure random numbers, okay? What is this? Okay, first of all, before playing with cryptography, it is necessary to be able to generate random numbers, but secure random numbers, cryptographically secure random numbers, cryptographically strong random numbers, which are built in arrays of bytes in a data type and not with numbers. Why we use them? Because these do not use any type of value from the device itself, like other randomized algorithms. With this way, we use algorithmic formulas that guarantee that no pattern can be found that will discover them. It's a totally, absolutely randomized number created without pattern, okay? It's a cryptographically strong random number, okay? How can we create it? Okay, it's so easy. We can use the sec random copy bytes method from the security of the keychain, okay, and all the things about the security framework in Swift. And then we can use something that is so good from Swift 5, the array of uint8, unsigned integer of 8 bits, an array of this Swift native type is directly convertible to data type with the constructor, okay? As you know, you can convert a double number in int or int in double, okay? You can put an int number, double parenthesis, in number parenthesis, and then you have a direct creation, a direct transformation between types using the constructors. Okay, an array of uint8 has direct transformation with data type. If you have an array of uint8, you can put this data in data constructor and you are making a new data type, a new row bytes data type. We are creating an array with empty values, with zeros. Then we send to sec random copy bytes with the property ksec random default. Then the count bytes we desire, and then the reference with the ampersand of random bytes. Then sec random copy bytes returns in random bytes the cryptographically strong random number. Okay, it's so easy to make it. With this, we can use data encryption. For example, when you have to store a password, you must store not in plain text, please. You must store in hash, with a password hashing. Even the best way to do it is with HMAC 256 algorithm. Okay. HMAC, what is HMAC? It's an algorithm that uses a key to ensure that hashes are not are not repeated in their calculation for the same data. One of the most important problems when you calculate a hash is the collision, okay? When you have a collision in a hash calculation, it means you have two different datas that has the same hash, okay? And it's a great problem. To try to resolve this, HMAC put a key when you calculate the hash. Because of this, if you don't have the key, you cannot check the data, you cannot create the same hash for the same data, because for validate a hash, you must have the data and the equivalent and the key we use to create this hash, okay? How can you do it? Okay, using CryptoKit, this is the easiest way. You receive a key that can be a strong, cryptographically strong random number we create before, okay? We use this number and then we send as a key, okay? With this, CryptoKit creates with the data a symmetric key, and then with HMAC HE 256 dot authentication code, we obtain the hash for a string using the key, okay? And then because a code authentication code returns an array of uint 8, then we are returning in the constructor of data, okay? Then this data can convert to, for example, a base 64 string, for example. How can you use this function? Okay, in this way, it's so simple. Random key generator of 2048, then HMAC 256, CK, string and the key, and then obtain the base 64 encoded string. Then this base 64 encoded string is the value you must to store, okay? Then, how can you validate a password? Okay, the validation of a hash is to convert the plain text password, making the hash again with the same key, and then you compared the encrypted hash with the new one, and if it's the same password, okay? Why we use hash? Because hash is an algorithm that avoids to make the transformation, the decryption of the data. When you have the hash, it's impossible to know the data we are hashing, okay? This is the security way to ensure this feature, okay? When you want to validate an authentication code for hash, the only thing you need is to make HMAC HE 256 is validated authentication code, and then when you put in authenticating the plain text password that the user introduces, with this you are comparing the H0CK, that is the hash, with the value in plain text in Catena, okay? And then using the key, okay? The key for validate the hash, okay? It's so easy. Next step, we are trying to make encryption, okay? AES 2056 GCM encryption. The AES GCM is a Galois compteur mode, okay? It's a cipher mode that is one of the most widely used for its performance and efficiency, and it's recommended by Apple. It requires two keys, a cryptographic key as well as an encryption authentication data. You need two values to make this encryption. If we do not have both values, we cannot decrypt the content, okay? The operation is an authenticated encryption algorithm designed to provide both data authenticity, the integrity of the data, and the confidentiality, okay? Makes these things all together. GCM can take full advantage of parallel processing. If we have many threads, the algorithm uses these many threads, and implementing GCM can make efficient use of an instruction pipeline of a hardware pipeline. For example, when you have many threads and have an encryption engine like an M1, for example. Okay, how can I do it? It's so easy with CryptoKit. You have to create a sealed box, okay? With try, you are using aes.gcm.seal, and in this seal you have to provide the data you want to encrypt, the key you are using, and the authenticating data, okay? With this you obtain a sealed box, and when you access to combined property, you can extract a encrypted string. You can storage on base 64, for example. Okay? How can I decrypt this? Making the same, but in this time you are creating a sealed box, okay? With AES GCM, you use the initialize function sealed box with the combined data you are storage before. With this combined data, you are creating a new sealed box, and then you can open, providing it the sealed box, the key, and the authentication. And then it returns the data decrypted. This data you can convert with string, for example, string data with the data that returns this function, and in .utf8, okay? And with this you can see the new data decrypted, okay? It's so easy. It's not hard. Next step, Swift code security best practices. One of the things we are so important is to try not to show any sensitive data when your app goes to background. Because of this, the app makes a screenshot of the last screen it showed, and then your application, the screens, when you buy from one application to another, in this screenshot you can see maybe any sensitive data. Well, this could result in an unintentional capture of sensitive data, and we have to do some process to control it. What process? For example, if you use SwiftUI, you have a new modifier, .privacySensitive. You can put in any view. If you put this modifier, when you put the app in background, this data will be blurred, okay? And the user cannot see. It's so simple. But when you use another framework, or maybe if you use SwiftUI or even UIKit, we can capture system notifications, okay? You can capture the system notification, UI application will resign active notification, and did become active notification. Will resign is when the app goes to background, and did become active is when the app is going foreground. Well, with this, you can use this code. You make an observer to UI application will resign active notification in the main queue, and then creates a black view controller, and then put it on your present it in the root view controller. Okay, with this you can create a UI view controller that puts in front of your screen at the moment you are entered to background, your app screenshot will see blank. Okay, how can you dismiss this blank interface? Okay, capturing the another notification, did become active notification. In this, you make UI application, shared Windows first, root view controller, dismiss, and then the black view controller dismiss it, and then you can see the app when you enter in foreground again. Okay, that's so easy. Another thing is to avoid backup copies of key files. An iTunes backup, for example, can allow access to files in a very simple way. Okay, since iOS 8.3, Apple does not allow access to the sandboxing. Okay, but if you make or someone makes an unencrypted backup in iTunes of your devices, they come to extract data, compromise your security or your privacy. We have to configure the resource of the URL file itself. Okay, in this way you prevent that a file will be included in iTunes backup, okay, or maybe iCloud. It's important to remember that except jailbreak, the only way to explore the file system on an iOS device is through an iTunes unencrypted backup. We should never trust any device that is not ours, okay, when it shows us the alert to trust in this device. How can I do it? Okay, it's so easy. You have to modify the values of the URL type by adding a URL resource value object, like this. If I want to write a data1.txt, you have to config URL resource value is excluded from backup, true, and then set resource value. With this, your data1.txt are not included in your iTunes backup or in your iCloud backup. Final conclusions. As developers, okay, we are always behind the system. We have the responsibility. With great power comes great responsibility, as you know. If it is vulnerable, so is our app, but doing our job well is a guarantee for our users, okay? Everything we have said should be a layer that is part of your day-to-day, part of your development routine. Make your APIs, make your helper functions, make all the things you need to secure your application, make a Swift package, for example, and use it in all your apps to ensure you make the best secure coding in iOS or other Apple systems. Being responsible for security, data, and good development practice will make our developments better and more efficient. And don't forget to update any third-party libraries you use. But maybe it's better not to use it. Maybe a better option, if you can, is try to go completely native, because many times, and don't forget this, we don't know who is behind a third-party library, and we are relying on their good faith and good security practice blindly. That's not a good option. Remember, don't trust anyone. Okay? And that's it. Thank you so much. I hope you like this talk, and I hope you are now, you know Kung Fu in security, and then your code will be more secure. Thanks to Conf42 for the opportunity to make this talk, and as I said always in my podcast and live streams, best regards and good Apple coding.